Hello Theory 4 students once again. This lecture is being recorded on Friday, April 3rd in the year 2020. And today we are going to be continuing our discussion of set theory or atonal theory. And today specifically I'd like to talk to you about two things. Number one, the term is called equivalence relations. And number two, the second thing I'd like to talk to you about is going to be something called modulo 12. Now, I don't want you to panic. These terms sound pretty confusing, perhaps, but they really are not all that bad. In order to start talking about equivalence relations, I need to let you know that set theory or atonal theory implements four different equivalence relations. It kind of assumes that these relationships are true. And let me go ahead and dim the lights so we can take a look at what these four equivalence relations are. First of all, in equivalence relations, we have something called octave equivalence, then enharmonic equivalence, transpositional equivalence, and finally inversional equivalence. And although we just take this for granted, especially when we start studying music our freshman year or in Theory 1 or whenever, octave equivalence is actually a pretty powerful property about music. Octave equivalence allows us to say that a familiar tune such as Happy Birthday, or really any tune, will be the same tune no matter what octave it is played in or sung in. Okay? So for instance, I could sing a little bit of the beginning of Happy Birthday, Happy Birthday to you. Then I could also sing it in another octave, either really low or really high. Happy birthday. That's not going to work very well. Anyways, because it's going to be in the same octave, we recognize that it is the same song, Happy Birthday, no matter what octave it is performed in. Secondly, enharmonic equivalence. This lets us know and tells us that, and again, we don't think about it very much, but that F sharp, for instance, is equivalent in sound to G flat, and A sharp is equivalent to B flat, etc. Enharmonic equivalence goes into harmonies and it goes into keys as well. So for instance, we know that an E major triad is enharmonic with and sounds identical to an F flat major triad. The property or the equivalence relation of enharmonic equivalence allows us to say that. It also works with keys. So for instance, if I played a minor tune, whatever a minor melody it might be, if I played it in B flat minor, it would sound no different and our ear would recognize it as just the same as in the minor melody that's played in A sharp minor. Because the key of A sharp minor and the key of B flat minor are enharmonically equivalent. The last two that are listed up here on the screen, transpositional equivalence and inversional equivalence. The last one, especially inversional equivalence, is more specific to atonal music, 20th century music. Transpositional equivalence, number 3, you can come up with an analogy in regular tonal traditional music. Transpositional equivalence, for instance, lets us say that if I play the tune or sing the tune Happy Birthday in the key of C, for example, and then I also play the tune Happy Birthday or sing it in another key, such as the key of F, we can recognize and know that those two songs, they're both Happy Birthday. They are one and the same tune. So that's a little bit about transpositional equivalence. Inversional equivalence is a little bit trickier to understand. Inversional equivalence basically says that if a song or a tune with its certain intervals is played upside down, in other words, it contains the same intervals as the original tune or melody that we're familiar with, but the intervals go down instead of up, or up instead of down, that even that type of song would be equivalent to the original song because the intervallic content of the song, in other words, the distance between the pitches, is identical. It's just that the direction is different. In one version, the intervals go up and then down. In another version, the intervals are the same size, but they go down and then up. So again, that one's a little harder to wrap your mind around, but it is true. Inversional equivalence does hold, and it is a property that is true in atonal music. You may recall that a few lectures ago I talked about pitch classes and how a pitch, regardless of its octave or how it is enharmonically spelled, belongs to one and the same pitch class. And on the bottom of page 506 in your text, there is, again, a nice green table to illustrate the various pitch classes. There are a total of 12 pitch classes, and they are always numbered 0 through 11. Be careful, they are not numbered 1 through 12, they are numbered 0 through 11. And C is the pitch class that starts us on 0. C equals 0 in this fixed integer notation system for pitch classes. Another thing that we talked about regarding pitch class is that it doesn't, as I said, it doesn't matter what octave a pitch is in, nor does it matter how it is spelled enharmonically or not. As long as the pitch sounds the same, the pitches belong to one and the same pitch class. So for example, with pitch class 0, C, any C on the keyboard belongs to pitch class 0. And B sharp, any B sharp on the keyboard is also going to belong to the same pitch class 0. And now we maybe can understand a little bit more why C and B sharp, no matter what octave they're in and no matter how they're enharmonically spelled, will all belong to one and the same pitch class. Because we are using the properties of octave equivalence and enharmonic equivalence to get the 12 pitch classes. We can reduce all the notes that are on a piano keyboard, for instance, down to just 12 pitch classes. And so, for example, we have pitch class 3, which is D sharp or E flat. You could spell it as F double flat, for instance. All of those pitches would be in pitch class 3 because it doesn't matter what octave they're in and it doesn't matter how they are enharmonically spelled. Octave equivalence and enharmonic equivalence holds true. Now the 12 pitch classes can be distributed around a circle, kind of like the face of a clock. And if you look in your text on the top of page 510, you'll see a circle with all the 12 pitch classes arranged around it, kind of like the face of a clock. We know that on a clock there are 12 spots. We know 12 o'clock is here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc., etc. But instead of the numbers of a clock, we have on this circle the pitch classes that are arranged in 12 increments. So we're starting with C equals 0 at the top, and then C sharp is the same thing as 1 o'clock, D is like 2 o'clock, D sharp is 3 o'clock, etc., etc. You'll notice that when we move clockwise around this particular circle, and by the way, it's not called a circle of fifths, because these pitches are arranged not in perfect fifths as you go clockwise around the circle, but they are arranged in half steps. So C to C sharp is 1 half step. So that's why C sharp is pitch class 1. C to D is 2 half steps from C, going clockwise around the circle. So that's why D is pitch class 2, and so on and so forth. So they're all divided and kind of dispersed around this circle in semitones, or half steps. Okay. So that means we know, for instance, that the distance from E to F is 1 half step, and the distance from D to F sharp is 1, 2, 3, 4 half steps, etc., etc. The next screen that you can see here is another one of these pitch class clock faces, so to speak, but instead of letter names for pitches, we have translated all of the letter names of the pitches in the diagram that's right above into pitch class integers, and you can see again C is at the top and C is pitch class integer 0, and we have them all arranged around the circle. So, if you go clockwise around the circle, you are going up by a half step each time. And if you go counterclockwise around the circle, or this way, then you are decreasing, you're going down a half step each time. Okay. This diagram is actually very useful because it allows us to see how to apply some basic arithmetic operations in what's called a modulo 12 system. We already know a little bit about, we're somewhat familiar, I should say, with a modulo 12 arithmetic. By the way, modulo 12 arithmetic, it's usually abbreviated mod 12, M-O-D, and then 12, rather than writing out the whole name modulo 12 arithmetic. And it's based on groups and distances, so to speak, of 12. So let me give you a familiar but really concrete example. Suppose that it is 10 o'clock in the morning, and let's say you're hungry, but you can't eat lunch for another 3 hours. Let's say, for instance, you have a class from 10 to 11, then another class from 11 to 12, and then another class from 12 to 1. For 3 hours you can't eat. Some of you may have schedules like that, who knows. Anyways, so if you're right at 10 o'clock in the morning and you're hungry but you can't eat for 3 hours, at what time will you be able to eat lunch? Well, that's not hard to calculate because you know that 3 hours in the future, or 3 hours, in the future from 10 o'clock is 1 o'clock in the afternoon. It is not 13 o'clock in the afternoon unless you're using, military time. But let me go back to the diagram of the clock face once again with the pitch class integers. So if we're here at 10 o'clock in the morning and we're hungry and we know we can't eat for 3 hours, 1, 2, 3, that means the soonest and earliest we can eat is 1 o'clock. So all you have to do is add, 3 hours, or in this pitch class system, 3 semitones. And in this case, 10 plus 3 actually equals 1, not 13. In a modulo 12 system, our final answers, when we add and subtract pitch class integers, our final answers can only be between the numbers 0 and 11. Okay. You cannot have any answers that are larger than 11. You cannot have any answers when you add and subtract pitch class integers that are smaller than 0. Every single answer must be 0, somewhere between 0 and 11 inclusive. That means including 0 and 11 as well. So I guess I'm trying to say that adding and subtracting pitch class integers kind of works the same way as telling time around the clock, although when we add and subtract integers, when we add, I should say, we go clockwise around the circle, and when we subtract, we go counterclockwise around the circle. Okay. Also, it is important to know that the range, as I said, is between 0 and 11. No answers or numbers can be lower than 0, and no answers can be higher than 11. Now, what happens though, for instance, if you need to add pitch classes 10 to pitch class 11? Well, in normal arithmetic, traditional math, you would get the result or the sum of 21. But 21 is not between the numbers 0 and 11, and it doesn't occur on our pitch class clock face. So when you have numbers, when you add and subtract integers, when you have numbers that are larger than 11, what you do is you subtract 12 from your answer, or subtract 12 as many times as you need to from your answer until you get a final answer with a number between 0 and 11. So for instance, 10 plus 11 we know is 21, but that's too large. It has to be between 0 and 11. So what is 21 minus 12? Well, it's going to be the same thing as going from 11 and then going back 12 half steps. So 21 minus 12 actually equals 9. Hang on a second. Let me pause for a second. I think it'll help me to write this out. So we're adding pitch class integers using the mod 12 system. 10 plus 11, as we know, is 21. Okay? Subtracting 12, because 21 is too large, it's beyond the numbers between 0 through 11, gives me the answer of 9. So in mod 12 arithmetic, the pitch class 10, and you add 11 to it, or 11 semitones to it, gives us the final answer of 9. Now, let me go back to the diagram. Okay, so we're starting here at 10 and we're adding 11. So let's go clockwise around the circle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We end up at pitch class 9. That's a little bit about how to add pitch class integers in a mod 12 system. Okay? Let me go to the other screen. And again, if you have this, I think it'd be most helpful if you have this diagram, which is on page 510 in your book. If you have it open to that page and you can look at this, the computations and just the little arithmetic that I'm going to be doing on the other screen will probably make a lot more sense. Let's try a few more possibilities for adding pitch class integers together. Let's try 11 plus 2. 11 plus 2 in traditional math, as we know, is 13. But 13 is not a number between 0 and 11. So we have to subtract 12 from it in order to get it between the range of 0 and 11. So 13 minus 12 in this case equals 1. So using our pitch class circle, clock face, starting at 11 and going 2 more digits to the right, clockwise, gets us to 1. That's our final answer. Okay? So in this Mod 12 system, this fuzzy math, 11 plus 2 is the same as 1. Let's see how this translates to pitches. So for instance, we know pitch class 11 is B, represents the pitch B, and if we add 2 half steps to B, would we not get up to C sharp? Okay. 2 half steps higher than B gives us C sharp, and the pitch class integer for C sharp is indeed 1. Let's try another one. How about pitch class integer 6 and going up 6 half steps from that? So you can think of pitch class integer 6 is F sharp or G flat. And if you count on the clock face, 6 half steps clockwise around the circle, 6 half steps above an F sharp happens to be a C. Now, we know in traditional math, 6 plus 6 is 12, but 12 is not between the numbers 0 and 11. So we have to subtract 12 in order to get it within that range. And 12 minus 12 is the same thing as 0, and we know that pitch class 0 is equivalent to C. By the way, adding 12 or subtracting 12 in modulo 12 arithmetic and in atonal music is the same thing as basically going up or down an octave. Now, why is 12 the magic number for an octave? Well, if you look at a keyboard or any picture of a keyboard in your book, you should find that there are 12 half steps between one C on the piano and to get you to the next C up higher or down lower. There are always 12 half steps within the span of an octave. Let's do a few more arithmetic problems, this time subtracting pitch class integers. So I'll get rid of some of these and I'll come up with just a few more short examples to go through so you can know how to add and subtract pitch class integers. Let's say we want to do 10, pitch class 10, and we subtract an octave or 12 semitones. Well, we know in traditional math, 10 minus 12 is negative 2. But negative 2 is not between the magic numbers 0 and 11. So in this case, we need to add 12 to our answer in order to get it within the range of 0 to 11. And if we add 12 to negative 2, our final answer then is positive 10. And let's think about this pitch-wise. A pitch class integer 10 is the same as B flat or A sharp. If we subtract an octave from B flat, or if we go down an octave from B flat, do we not end on a B flat again? And because of octave equivalence, the pitch class integers are the same. This lower B flat belongs to the same pitch class as that higher B flat, which is 10. And maybe one more. Okay, let's start at 4 on our pitch clock face, and let's subtract 10 semitones, or 10 half steps. Traditional math says 4 minus 10 is negative 6. Once again, negative 6 is too low. It's outside the range of 0 to 11. So if we add 12 to negative 6, we will get a final answer of positive 6. So in pitch class atonal music, 4 minus 10 actually equals 6. 4 minus 10 equals 6. Now, some of the problems on your next homework assignment, which is going to be out of the workbook, are going to ask you to reduce certain integers that are either too big or too small. They're not between 0 and 11, but the instructions will ask you to reduce the integer to an integer mod 12, which means within that magic span of 0 to 11. That's what we're trying to get all of our integers within that range. Okay. So for instance, if I gave you the integer 26, how would you reduce that into the range of 0 to 11? Well, 26 is larger than 11. It's too big. So what we do is we subtract 12. And 26 minus 12, we get, it should be 14. Well, but 14 is still too large. It's not within the range of 0 through 11. Well, then what you do is you just keep subtracting 12 until you get a number within the targeted range. So 14 minus 12 is 2. And actually then this 26, if you reduce this integer to the mod 12 system, my final answer for this is going to be 2. And if you were to look at the pitch class clock face, and you start, well, basically this is saying we're going down 2 octaves from whatever pitch 26 would be. And 26 is going to be the same pitch class, or the same pitch as the pitch class 2. So pitch class 2 is D, 26 is just a theoretical D that's 2 octaves higher. Okay, let's try another one. Let's see if that we can get, starting with negative 16. How do we get that, how do we reduce that integer or get that number, that integer between the range of 0 to 11? Well, since it's too small or too low, what we do is we add 12. And it looks like we only need to add, well, let's see, let's look at this. If we add 12 to negative 16, we get negative 4. Well, that's still not within the magic range, so I need to add 12 again. You just add or subtract 12 repeatedly to a number that's outside the range to get it within the range. And this turns out to be positive 8. Okay? So, getting this integer, negative 16, into the realm or into the range of mod 12 between 0 and 11, my final answer for this would be 8. And there are several exercises for you out of your workbook on the homework for next week, which will give you lots of practice for this. Alright, let's move a little off of the logistics of mod 12 arithmetic, and let's go ahead and apply it and put it to use in terms of transpositional equivalence and inversional equivalence. Because in order to compute transpositional equivalence and inversional equivalence, you have to use mod 12 arithmetic. Okay, the transposition operation. This is actually something, it's an active thing, something we do, transpose. The transposition operation in atonal music is actually designated by a symbol. And you'll probably see some of these symbols in your book, probably starting around maybe page 511 and further. But the transposition operation is designated by the symbol capital T with sub n, lowercase n. Okay? Capital T with a subscript lowercase n. Okay. Now, to transpose a pitch class set, let me start with a pitch class set. I've been using this one as an example for many lectures. Let's start with the pitch class set 7, 8, and 11. In fact, that set is already in normal order, so I'm going to put it in square brackets. Okay, so we have a pitch class 7, 8, 11. In order to transpose this pitch class, what you do is you transpose, you add the transposition number, and that's what this is. The subscript of the symbol T sub n, this is the transposition number. Okay. T stands for transposition, N is the transposition number. So what you do is you add the transposition number N to each member of the set in turn using mod 12 arithmetic. And by the way, N always refers to the number of half steps you are transposing a pitch class set. So it refers always to the number of semitones. Okay? So let's say I had a problem that looked like this. Let me make a little more space off to the side. Let's say we have T sub 1 of the pitch class set 7, 8, 11. What this problem means, or what this symbology is telling me to do, it's telling me transpose the pitch class set 7, 8, and 11 up one semitone. Well, okay, that's pretty easy. All I have to do is just take the number of semitones, the transposition number right here, and add it to every member of the pitch class set. So 7 plus 1 is 8. By the way, remember we're using mod 12 arithmetic. And 8 plus 1 is 9. And 11 plus 1 is 12. Oh, but 12 is too large. It's got to always be between 0 and 11. So subtract 12, an octave, from 12, and you get 0. So in fact, in mod 12 arithmetic, 11 plus 1 is 0. And transposing the set 7, 8, 11 up a half step gives us the pitch class set 8, 9, 0. If you want to think about this and look at it in terms of actual pitch letter names, we know, for instance, these pitch classes 7, 8, 11 refer to the pitches G and G sharp and B. What happens if you transpose G, G sharp, and B each up a half step? Well, you should get G sharp, you should get A, and you should get C. And that's exactly what we have here. We have pitch class 8, which is G sharp, pitch class 9, which is A, and 0, which is pitch class 0, which is C. So that's all we've done. We've just raised all the pitch classes in this set, we've raised them all up a half step. So we added a half step to each of them to get the next pitch class. Now, transpositional equivalence means that these two pitch class sets, 7, 8, 11 and 8, 9, 0, they are said to be equivalent. They are transpositionally equivalent. That is to say, they are the same in every way except for being a half step apart. So these two pitch classes are really, they're just alike in practically every way except they're just a half step apart. And so we'll find out in a future lecture that these pitch classes, they actually belong to the same family. They're said to be equivalent, so they belong to the same family. Finally, I guess one last thing I could say about transpositional equivalence is that transposition does not change the essence or the intervallic content among the pitches in a set, right? The distance between all of the pitches and the pitch classes in the set are still identical. Nothing has changed there. We just kind of raised the pitch level and that's all. That's what we do transposing regular music, right? You play something in the key of D and you want to take it up a whole step, you just raise everything to the key of E, but all the relationships and the intervals between the pitches are still the same because you say you were started in D major, you're just going up to E major. What does this tell us practically now with actual music? Let's take a look at an example in your book. Remember the pitch class sets 7, 8, 11, and 8, 9, 0, or if you want to remember the pitch letter names, G, G sharp B, and G sharp A, C. So on the bottom of page 505 in your textbook, take a look at the first three notes of this example. They are B, G sharp, and G natural. Now they're not in normal order, but that's okay. There's still those three pitch classes, B, G sharp, and G natural. If you were to turn the page and look at the top of page 506, if you focus in on measure 10 specifically in the right hand, you'll notice that the three pitches in this measure are C, G sharp, and A. Well, aren't those three notes the same pitch classes that we got when we transposed the original set G, G sharp, B up a half step? Yes. So what we can tell now, and what we can understand, at least in this short atonal passage, is that the three pitches at the beginning of the piece, that pitch class set, is related to, it's considered to be equivalent to these three pitches in the right hand of measure 10. Okay. That helps us to see that the composer is not just necessarily throwing random notes up on the staff and composing whatever he or she may just feel like, but the composer is actually using some pitch class sets that are considered equivalent or certainly related, closely related to the initial pitch class set of the piece. And we would not be able to understand this, and we would not be able to see this if it were not for things like transpositional equivalence and knowing how to work the mod 12 system and so on and so forth. So, observing and finding relationships between groups of pitches in atonal music comes at a cost of some pretty high calculations. There's a lot of computation that has to go on. And we're going to finally get to the end of the computation in another lecture or two. But for now, just kind of enjoy it while you can, and you can start finding things that you would not otherwise see in atonal music. By the way, I should also not forget to mention that normal order is a really big part of this. When we have sets that are all in normal order, we can see that they are transpositions of each other much more easily than if the sets were just in haphazard random orders. Let's do just one more transposition example, and then we'll move on to inversion, and that'll hopefully be the last thing that we need to do. Alright, so let's say I want to transpose this particular set, 7, 8, 11, up 2 semitones. Raise it 2 semitones. So then the symbology would be T sub 2 of the pitch class set 7, 8, 11. That means transpose this pitch class set up 2 semitones. So in order to transpose a pitch class set, what we do is we add the transposition number, or the number of half steps, to every member of the pitch class set. And what we will end up with then, again using mod 12 arithmetic, is we will end up with the pitch class set 9, 10, and 11 plus 2 in mod 12 is equal to 1. 9, 10, 1. What are those pitches? Well, 9 is the pitch A, 10 can refer to B flat, or A sharp, however you want to spell it, and then 1 is C sharp, or D flat. Let's see if there is one more. In fact, I'm going to spell the C sharp in this case as a D flat. Doesn't really matter, but this will make more sense. I'd like to look at measure 3 of the opening example of chapter 27 in your book, and I'll show that on the screen right now. Okay, so in measure 3 of this example, again, I'm on the bottom of page 505. You can see that I have circled this half-note chord that comes right in the middle of the measure. Check out what its notes are. They are B flat, A, and D flat. So we know that this chord is transpositionally related to the opening 3 notes, melodic notes, of the atonal example. Again, we would not be able to understand or see that otherwise if it were not for normal order, and if it were not for transpositional equivalence and the mod 12 arithmetic system. Alright, so I don't want to make this lecture too long, and I'm just going to try to finish up by talking about inversional equivalence and how to invert a pitch class set. Remember, inversional equivalence is one of those 4 fundamental equivalence relations we talked about at the top of the lecture. Now, in atonal or set theory, pitch class inversion is defined as subtraction from 12 in the mod 12 arithmetic system. And again, what does 12 represent? It represents basically the space of an octave. Okay, so to invert a pitch class set, simply subtract each member of the set from 12. Okay. So again, let's take a pitch class set. Let's use the one 7, 8, 11 that I have been using again. And let's invert that pitch class set. And by the way, the official symbol for inversion in set theory is this symbol. It's T sub n I. And really what this refers to is it refers to a 2-step process. Refers to a 2-step process. What we do, we actually do this process in the reverse order of how the letters are indicated here. We actually invert the set first, and then after we invert the set, whatever numbers, pitch class integers we get, we're going to transpose that particular set up by the number of transposition, which will be given here as the lowercase n subscript. So it's a 2-step process. First of all, you take a set and you invert it. Now, to invert a set, what we do is subtract 12 from every member of the pitch class set. Okay? And so when we do that in a mod 12 system, 7 minus 12 is technically negative 5. But if we add 12 to that, then what we're going to get is 7. No, I'm sorry. Scratch this. Scratch this. Go back 30 seconds in your lecture. What we're going to do is subtract every member of the pitch class set from 12. We are not going to subtract 12 from every member of the pitch class set. We're going to subtract them all from 12. So 12 minus 7 is 5. And 12 minus 8 is 4 in the mod 12 system. And 12 minus 11 is 1. Okay? So the inversion of pitch class set 7, 8, 11 turns out to be the set 5, 4, 1. Now, one monkey wrench that kind of gets thrown in when you deal with inverting pitch class sets. Whenever you invert a pitch class set, it throws your pitch class set out of normal order. For instance, I know that 7, 8, 11 is in normal order. We have calculated that in previous lectures. But when I invert the set, that is, if I subtract all the members of the set from 12, and I get this result, the set 5, 4, 1, what happens is that it knocks my once normal order set, it knocks it out of normal order and makes it an unordered set again. So I'm going to use curvy parentheses rather than the square brackets to notate this inverted set, 5, 4, 1. It's an unordered set. It has been jarred out of normal order. That's what inversion does to a set. Now, let's talk about, let's do this is just a one-step process of how to invert a set. Let's do the full two-step process for inversion first and then transposition. Okay? So let's say, for instance, that I had a problem with this set 7, 8, 11, that I had a problem that said, let's find T11I of this set. Okay. That means invert the set, and then after that, the answer we get here, we're going to add the transposition number 11 to all the members of our set. Okay. So invert the set first. 7, 8, 11 are subtracted from 12, and I get 5, 4, 1. Now, what we have is we just have this operation. Transpose this set up 11 semitones, because we already took care of the inversion. And what that's going to give us is, well, 11 plus 5 is traditionally 16, but that's too large, so subtract 12 from that and you get 4. 11 plus 4 is 15, which is beyond our range, so 15 minus 12 is 3. And 11 plus 1 is 12. And 12 is a little bit too large, so subtract 12 and we get 0. Okay. So, my final answer for this initial problem, right here, T11I of the pitch class set 7, 8, 11, my final answer is the set 430. 430. Okay, what this allows us to say is that these two sets here, 430 and 7, 8, 11, those two sets are considered to be inversionally equivalent in atonal music. Inversionally equivalent. And again, that is to say that these sets are identical in every way, the 7, 8, 11 and the 430, except that the intervals between the pitches of the pitch class sets are going in a different direction. But the intervallic content among the pitches of the set is exactly the same between these two sets. It's just that the direction of the intervals are different. So, I guess in conclusion with inversional equivalence, we can say that inversion does not change the essence of a set any more than transposition does. Same intervals here as there are in this top set, except that where those intervals go up, these intervals go down, and where these intervals go down, these ones go up. It might not be readily apparent to the eye, because once again, this set is not in normal order as it would be in this case. All right, let's go through one more inversion of a pitch class set, that operation, and then hopefully that'll be enough to get you going for your homework assignment. So let's start over again. Let's say we want to find, again using our same pitch class set, 7, 8, 11, let's say we want to find what T6I is of the pitch class set. Again, this symbol here refers to inversion of a set, and it's a two-step process. Invert the set first, and then transpose your answer up 6 semitones. And that will be your final answer for the whole problem, or the whole exercise. So, subtracting all these integers of the original set from 12, once again, should give me a set that I got just recently, just a few minutes ago. So 12 minus 7 is 5, 12 minus 8 is 4, and 12 minus 11 is 1. Whoops. And again, inverting a set knocks the set out of normal order. It just throws it out of that order. Okay, so now adding 6 or transposing this set up 6 semitones will add 6 to every member of the set. And remember, we're dealing with mod 12 arithmetic. So 6 plus 5 is 11, and 6 plus 4 is 10, and 6 plus 1 is 7. Okay. So the final answer for T6I of the pitch class set 7, 8, 11 is the pitch class set 11, 10, and 7. Alright, we're getting towards the very end of this lecture finally. I know this is a lot of information. I always encourage you to, and please do, contact me if you have questions, if this lecture does not make sense in some spots. Also, if you need to go back and rewind and look at some of the sections of this lecture again, I think that would be very helpful if you need it. Obviously, we can't do that in real live face-to-face classes. So I will put on Canvas